this is actually one project that is related to the Facebook Faculty Award. So let me just first talk about some background and especially why we need to do the data compression. The motivation actually is just because of the because of the data, and then the data is too big, and then we do not just solve this one, use one computer, or even use one cluster at one place. So for example, if you want to use the deep learning to solve these big problems, and then you may not just use one GPU, then you may need to use other GPUs. And then if you use a lot of GPUs, and then you will need to do a lot of communications. So that will be something that you need to think about how you are going to deal with the large scale of data, because you cannot load all the data into the memory. And there's another way is that the data actually is already distributed, and then you do not want to put all the data together. Recently, there was a lot of people are interested in the federated learning. Actually, is one example is that for federated learning, actually, the name is like bring the code to the data instead of the data to the code. So the data is stored at different locations or different devices. For example, in the Gboard on Android, actually every device, every Android phone actually is one device. They have its own data, and all these phones, they will work together and trying to improve the keyboard recommendation. And there are other applications recently, actually a lot more applications, but here is just also some examples. Like NVIDIA actually also worked with another company for their healthcare, and then they want to do actually use the develop algorithms trying to solve the medical imaging problems. And then in that case, and you do not want to share this medical imaging because the medical imaging has some privacy issues, and then or you do not want to share this. So then in that case, how you are going to deal with the data communication between these algorithms. So that means like the distributed learning actually is very important, and then sometimes it's just because you need to do distributed learning, and sometimes it's just because you want to use distributed learning to get a fast algorithm. And there are several challenges in distributed learning. First one is the computation. So when we deal with the distributed learning, actually the computation is different from what we did on the just a single, like not non-parallel computing, or even like parallel computing with the shared memory. And so in that case, how you are going to how does the computational cost of distribution compare with the centralized computing? By centralized computing, I mean like you have all the shared memory, all this stuff. And also how to apply the distributed learning on even small devices like the cell phone or even other small smart devices. And also the second one actually is about the communication. And then for the communication, there are several difficulties or several challenges. For example, for every communication, we need to get some latency there, because you need to initiate a communication. So there will be a latency. And also another thing is the bandwidth. So uh, if the bandwidth is limited, then that means the transformation of the data is very slow. So in that case, how we are going to deal with the communication? And this is basically the time for all these. Like latency usually takes a lot of time, and then which is much larger than the time from the bandwidth. And of course, the bandwidth part actually depends on the size of the data that you want to transfer. So sometimes like you can increase the size of the data you want to transfer, and then that means the bandwidth can be a big problem than the latency. And then even no matter what, actually they are very slower than the flops most. And then for the communication, actually there are other difficulties. For example, the how to synchronize the communication and how to deal with the delay in the communication. Actually, there are a lot of people they are thinking about this even for the further learning, because for the further learning, only some devices are participants for during each iteration. And then, of course, there are other issues, for example, the memory issues and how to deal with the memory issues. And there are many others. I will not talk about this, but for today's talk, we will only focus on the communication. Basically, we will focus on how to make the communication fast. So uh, in order to make the communication fast or reduce the communication cost, there are several approaches. First, if we can reduce the communication rounds, right? So if we can reduce the iteration number, and then we can automatically reduce the communication cost. So that's actually related to the development of new algorithms or faster algorithms. So for example, if you can do accelerated algorithms or other adaptive algorithms, and then that's actually one thing. And then another one is that you can do more local updates, so like the local SGD. So instead of doing communication after each stochastic gradient descent, each node will do a lot of local SGD first, and then do communication. So in that case, you can just reduce the communication, and then by doing this type of stuff, you can also reduce communication. However, in that case, you need to think about how to develop this, how to show the convergence of the new algorithm. And then there's another one which is orthogonal to this. So reducing the communication rounds and actually the reducing the communicated bits actually is orthogonal, and they can be combined together to make the algorithm even faster. So in order to reduce the communicated bits, so if the data had some structures, and of course we can just use this structure. For example, if the data is sparse or the data is row rank, and then we can definitely use some structure of this. So for sparse, and then we can just only transfer the non-zero elements, or for the row rank, we can first do some decomposition, and then we just can transfer a small matrices. However, this is only works for special problems. And then if we want to develop general algorithm that can work for any data sets or any data set, we do not assume any special structures of the data, then we need to do just the data compression. And actually, the data compression only happens in the last 3 or 4 years. At the beginning, people just doing this SGD, and then just said, okay, what happens if I just do quantize the SGD? So for example, if I just do 1-bit SGD, so if the stochastic gradient descent value is positive, I just send 1. If this is negative, I just send 0. So if I just do this, and it turns out for some applications, actually the performance is very good. And then the reason is because many of these many of these applications is just for classification. So when they measure, they will measure probably the classification error. So that means that if you have some error there, it will not get too bad like classifications. So in that case, and starting that time, and people are thinking about it, we can just do compression. So we can compress the data, and then we just need to transfer only a few numbers. So for example, top K is that you just sort these values, and you just transfer the first K largest elements, and you just ignore all the other smaller ones. And then also QSGD is just the quantized quantized SGD. So you can just also quantize this into like 2 bits or 3 bits. So this is actually the quantized SGD can be unbiased. But actually, there are 2 groups of algorithms. I will separate them. So one is unbiased, and then so by unbiased, usually that means that you are doing like randomly quantization. So after that, the expectation will be the same as the original data that you want to transfer. Um, so for example, the random K is one example. You randomly pick K elements, and then you just send that K elements there. And then also there will be deterministic ones, which will be definitely biased. So for example, the 1-bit SGD, because if this is positive, you will just send 1, and the negative, you will just send 0. And also there are other different approaches. You can compress the data different ways. So there are also many other examples, and I will just talk about some examples later. Okay, so let me just go back to the problem. Oh, by the way, if you have any questions, and you can just ask. So the question or the optimization problem that we will focus on today is that we want to minimize a function which is fx and plus rx, even though in this talk we will just ignore the rx, because rx is usually it's a regularization term. It can be, for example, if we want x to be sparse, we will just choose like r is like a L1 norm. But for the f function, usually is a summation of many functions. And in this case, for example, we assume this sum is average of m functions and of fi, and each node will own which node will have the function fi. So the fi actually depends on the data, so that's why these functions are different, and then they are totally depend on the data set there. And then it can be also think about like for each fi, it can be an expectation or it can be just another average of the samples. So if you have the finite sample, and you can think about this is just the average of the samples. Or if you do not know the number of samples, or the sample can be very big, so you can just think about this is just the expectation. So this has a very general applications in many, especially recently, like image process, computer vision, image processing, or deep learning applications, and also statistic and machine learning problems. They can be formulated in this way. But I just want to mention here all these fi. So for each node, we have one function fi, and then this function will only stored in this in the specific node, and it will be not given to other nodes. And also because this is depend on the data. All right, so with these distributed learning problems, actually the first algorithm, just trying to solve this distributed algorithm, is that just do gradient descent. Because here we assume that f is differentiable. So by doing gradient descent is here. So there's a server or master node here. And also we have all other data nodes. So in this case, so each node, what we will do is like each node will receive the X, the kind of model, or we'll say the X from the server, and then update the compute the gradient. So you will compute the gradient Fi. After you compute the gradient Fi, and you send back the gradient Fi to the server, and then the server will take the average of the gradient it received, and then update the variable x. By doing this, and by doing this iteration, you can see actually there are two ways of communication, because you need to transfer the data, the x from the server to the node, and also you need to transfer the gradient from the node to the server. So there are two types of communications. And if we want to reduce the communication cost, so we need to focus on these two communications. And we will see how we can apply the data compression to this one. Next, let me just introduce some standard, or not just standard, like several state-of-the-art quantization algorithms. So the first one actually is it's just a very simple. It's just a compress the gradient, right? So for example, this is the non-compressed version, which is selected from the previous slide. And for the compressed version, is that okay? I just compress the gradient f, each gradient fi, so I get a gik, and I just send the gik to the node. So by the way, and here actually we only consider the transformation of the gradient for now, and then we will talk about the compression, the model part. Okay, so in this case, it's just the transfer the G, and then basically all these compressed framework is similar to this one, but the problem is like how can we just get this G, right? So we can just do compress the G gradient F. So this is the simplest direct compression, we call it. So direct compression is that, so I just quantize the gradient and send it back, right? Let's see how this algorithm works and will this algorithm converge or not, especially. So in this case, I will show that actually this algorithm will not converge to the optimal solution that we want for the gradient descent. The reason is here. So let's assume that all the node has the true solution. Let's just assume that we already have the solution, and actually this gradient descent or direct compression will leave x star. So for example here, if we just let xk equals x star, and then we just do minus the same thing, and then we just do quantization here. And because we have the quantization, then there will be error there. So that's actually all the thing here. The right hand side or the last term actually is the error for the compression. So if there is an error there, and then we cannot make the error become 0, because you can see here we have the step size, and here the step size is not 0, of course. If the step size is 0, then definitely we can make this to be smaller. So in order to make it converge, there are several ways. So first one is that you can decrease the running rate or the step size eta. So if you choose eta getting smaller and smaller, then in that case, what we can get is that the last term will definitely be getting like smaller and smaller. So let's hope that this will converge. And then by doing this, we can just think about this is just a gradient with an error. So it's very similar to the stochastic gradient descent. And then we know that for stochastic gradient descent, the convergence rate actually is smaller than actually is slower than the gradient descent. So that's why in direct compression, I would say not a good algorithm if you want to get more accurate solution. So this actually just by with diminished step size and for analyzing the convergence is not difficult. It's just to think about this additional stochastic in the stochastic gradient descent. So that's why stochastic gradient descent combined with the direct compression is very good because you will not you will not get the much slower. It's just make the variance larger, make the variance of the stochastic gradient larger. So you can still get the convergence. In that case, maybe you just need to choose a step size a little bit smaller than. Okay, so for all these convergence, there are several different different ways to show the convergence, and I will not talk about it here, but just let you know, like this is just not that difficult to show. So after that, and then people develop the error compensation. By error compensation is that because before the error compensation, so we just compress the value, and then the error compensation is okay. Since I compress this value, so I send some information to the server, but I still leave some information at myself. So what happens if I just add this error back to the next time? So instead of compress the gradient, I actually add the error that comes from the previous one. So actually, this is is the error from the previous compression. So after that, we add this one, and then we do the new compression, and also then we update the new error here. The error is just something you can think about. This is the original gradient or original information that we want to send, but this is actually the Q is the compressed version that we sent. So that's actually the E is the value that we did not send. So by doing this error compensation, actually the algorithm converges much faster, but it still is not that good. So the reason it's still here, it still comes from the error because we cannot totally cancel this error. So for example, if we can see, we do the same thing. So let's assume that we also start with the X star. And then even though we have the Q gradient F star plus E, and then we do the same thing as before. We add this term because we know that the summation of the gradient at X star is 0. So this term will be 0. And so this will be because this term will be 0, so this one will cancel. And then, however, we in this time we have two terms here. This term actually is the new summation of the error, and this one actually is the previous error. So if we do that one, and then in order to make sure that it converges, so there's two things. The first thing, if we can show that the summation of the compression error does not change, or then in this case we can show this will be cancelled. However, we cannot promise this one when we do the error compensation. We cannot make sure that the error does not change, right? Because if for each node you only know yourself, the value at yourself. So if the only thing that you can make it this make sure the sign will be the same. That's the only thing that you every time you have the same error. But that's not definitely not important. That's the impossible. And also the other ways that you can let eta goes to 0. So that actually tells us, okay, it's still we need to decrease the step size to get the accurate solution. So let's go to the. I use this one. Okay, so the next one actually is the difference compression. Difference compression is here. Actually, instead of just compress the compress the gradient or gradient add the noise, and what we do is actually we compress the gradient and the minus and variable. So the variable that we minus actually is h. So we will introduce a new sequence of HIK, and we hope that HIK will be close to the gradient. Evaluate the gradient FIXK. So because if HIK is close to gradient FIXK, then the compression the compression error can be very, very small. And in that case, and what do we get if the compression error is small? And then we can see here, everything here will be just a gradient. So that's actually the reason that we can make the algorithm converge without you choosing a small step size.
So I'm sorry, Min. Can you erase that annotation? Okay, good.
Yeah, I was trying to do, but I did not use this before. I thought this would be just on that slide, but
it's on your screen.
Yeah. Okay, so did I need a eraser? Okay, probably not. Okay, so in this case, and then the thing is that if we just start doing the same analysis, start with x star, and so we x star minus, and this is the summation that we have. Okay, and then in this case, we can see the only thing that we get actually is the error from the compression here. And of course, we just need to hope that we will have this result. We will hope the last term will go to 0. So if we want to choose a positive step size, and then of course we can get hi will be the gradient fi divided x star, and then in that case we will get x will be equals x star because the last term will be 0. By the way, the quantization that we choose is that if it's 0, if we want to quantize the 0, then this will be 0. Okay, so in that case, it's like, how can we choose the HIK, right? Because we do not know HIK, especially in this case, we do not know the gradient Fi at X star because we do not even know what the X star is. So that's actually one way to update. So one way to update HI actually is here. So when we update HIK, actually it's just add the quantized value to this one. The reason we update the quantized value add onto the HI is because we want to make sure that the server also have the HI. So HI is not just stored at the node, and also the server can compute the HI. So the server does not need to receive the HI. So we do not send HI, and then HI will be computed both in the node and also in the server. So for example here, because HI usually HI start with 0, So when hi starts with 0, and every time if we want to update hi, we just need to get the quantized value. But we know that the quantized value will be sent from the node I to the server. So that actually tells us that, okay, so we can the server actually can update hi. So we do not need to send hi. Since we do not need to send hi, then everything here is just we just need to send the quantized value. So that actually makes the communication cost like very small. So let me just go to the next algorithm. By the way, do you have any questions here so far? Because this is actually I think this is probably the most used quantization algorithms for now.
Hi, Professor. So I have a question for this update of HI. Are we assuming it is using the same quantization method as we update for the X?
Okay, so that's actually a good question. So the quantization actually is the same. So we will use the same. So that means for the server, you will just use the received quantized value and then to add this one. So the Q is the same.
Okay, I see. And then we only, as long as we have this HI, will converge to the gradient of Fi at X star. Then we will have this arrow to be 0. Is that correct?
Yes, that's correct. Yeah. So
Okay.
basically, for this one, so if we want to develop algorithms, and also we need to show and prove that the sequence hi will converge to the gradient fi at x star.
Okay, thank you.
And also, of course, the Q actually does not have to be the same for each node. Like each node, you can choose different Q. But so the quantization only happens at the nodes. So the server does not do any quantization for now.
I see. Thank you.
So these are the quantizations. And then next, I'm going to talk about the two algorithms. I combined everything together, and I'm going to talk about two algorithms. The first algorithm, DOR, actually will be just on the deterministic case. So we want to make sure that we can converge to the optimal solution. And then the last one actually is the error compensation with like momentum. Actually, in that case, we will only consider the stochastic, but in that case, we will consider the stochastic with a momentum or accelerated versions. Okay, so let's just focus on the first one. So when we talk about the previous ones, we only consider the compression that only happens at the worker node. So only worker node compress the value, and then the communication from the from the server to the worker is not compressed. So we can just also do the apply these techniques and to the master node and then to send it back. And then the good thing is that actually it will be much easier to do to compress the data transferred from server to the node. It's just because in that case, we can just do not transfer the x. We just transfer the difference of the x. Or so we will just the server will just do the average, and after the server does the average, and then the average will be sent and we done quantization and will be sent to the and will send to the nodes, and the node will update the x. So this is the main framework for this DOR is that the worker actually sends the compressed the gradient residual. So we call this is a gradient residual. So that's actually the reason why we have double residual, because we are not compress the gradient, we just compress gradient, the minus another value. So that's why we call it a residual. And also the master node will just broadcast the compressed model residual. So it's just to update the model. And then you will be more clear when I show the next slides, talking about the algorithms. So actually the algorithm, the red part actually is from the compression from the first server one and the node one, and the blue part is from the server. So for this algorithm, every time you just choose a sample. So you sample GI. Every worker node will be just first do a sample stochastic and find their stochastic like GIK. And then after you find the GIK, what you do is that you just find the gradient residual. After you compute the gradient residual, you just compress the gradient residual. So after you compress the gradient residual, and then you just update the HI. So this is how we update the HI, because the HI is the new sequence. HI is trying to check the gradient. And then actually everything here is not in the big bracket is that we do not compute this one. So but it's just to put it here to show, because we will not have any G hat here on the work node. And after that, you just send this compressed value to the master node. Okay, so when the master actually receives all the compressed value, the master will just take the average. So after you do all these average, and then what you do is you update the G. So this is actually something that in the previous Diana actually that we want to find the average. After we do the average of the compressed value, and we need to add back to HK to make sure this is the approximation of the average of the gradient. Okay, so that's why actually G hat is here is probably is an approximation of the gradient. Okay, so after that, and also the master also need to do the computation to update the H. And you can see here, H actually we just do when we update this H, we just update the averaged version. So it's not that means that we have to do n times. Okay, so we just need to do one time, because we do this on the average version. And after that, there are two ways to do. So you can directly compress the G hat. So one way that you just directly compress G hat. If you directly compress the G hat, this one will also goes to 0 because if the algorithm converges, and then in that case, actually, in this case, actually, we assume that we do not use the stochastic version. If we use the deterministic version, in that case, we do not need to do all these blue parts. We just compress the G hat. So after we compress the G hat and send the Q hat to the worker, this is one way. However, if the node actually uses a sampled stochastic gradient, so we cannot make sure that G will go to 0. We cannot make sure that G hat will go to 0. So in order to do that, what we do is that we use error compensation here. By doing error compensation, we can make this algorithm like much more faster though. So that's actually the blue part is the error compensation part, with actually probably additional parameters like gamma and eta here. So this is the main algorithm for the door. So we can see actually there are some parameters here. We have the alpha parameter, which is used to update the H. By the alpha actually can be any number. Usually we choose number which is close to 1 in the numerical test. Even though in the theory alpha sometimes need to be small. And then there's the alpha and also the beta, because after everyone received the Q hat, you can see here Q hat actually is all the gradient information actually has already with the gamma actually with the step size with the running rate here. And then but here we still need to decrease a little bit of the way choose beta, or actually we can put the beta inside these values. So beta can be this parameter actually can be removed because every node will update the same x hat, because x hat is the same. So with the same x hat, and you update the same Q hat. So that's why the output will be any x hat, because all the x hat will be the same. Okay, so let's just talk about some results, and then before that, let's just talk about some compressions. And in this case, actually in the door, actually we assume that the compression is unbiased. and then with some here is like we call it contracted. The contracted is that here, so that means that if for any x, actually for any x, and we know that the variance of the compression has to be smaller than the norm of x. And this is reasonable because when x is small, and then we do not want the compression error to be small. So in this case, we can just choose then as probably a similar size of the quantization. And also, this will be good is that if we just put a scale on these variables, and then this will not change the error here. So because if you put a scale on x, and then we can see here, this will be the constant c will be the same. So there are several examples, and I will not talk too much about this. And but I will just focus on the last one because that's the one that we used, and we found that this quantization is very good in the numerical test. So for the p norm, or we can say like infinite norm quantization, the infinite norm quantization is that if we are given a vector x, so we will just quantize this element wise. But so for every element, and we will just randomly pick one value as a Bernoulli random distribution. So every will be just the 1 or 0. Okay, if this is chosen to be 0, then that means that we usually will not send this value. But if this is choosing to be 1, and then we will keep the sign of x. So this is very similar to the sign SGD, and also combines another quantization because we can put sign 1 to be 0. By doing this, it's just want to make sure that with the algorithm, the quantization will be unbiased. However, we add additional term here, which is the length of the x, and this is very important. By doing this, by just computing this length, it will not take too much does not take too much storage, especially when x is very large. So for example, if x is a 1,000 variable, so in that case, we just need to compute one variable, and then we can just transfer this with like even like 16 bits. So we can choose a little bit more accurate for the norm. And then if by just doing this, actually we can get a much better result. So that's actually very important part to put the size of x here. And by doing this, actually, we can find the C value. Like C value can be computed. So that's why you can see here, in this case, that's what we can see if P equals infinity, and then this C will be the smallest one. And also, infinity is also easy to compute, just to find the largest value. All right, so that's how we talk about the compression. And other standard assumptions that for the convergence of the algorithm. So for example, we need for stochastic gradient, we need this to be unbiased, and also the variance is also bounded. And then we assume the function is error smooth. That means the gradient of f is error Lipschitz continuous. And then for one of the results, we will assume the function is strongly convex. And so even though like the result is also works for non-convex functions. This is the result first for the linear convergence. So if the function is strongly convex, and we can show the linear convergence, and then probably you can see here, actually there are a lot of very complicated parameters here, just trying to show it here. But if we can, like the beta, actually the steps after we compute the gradient, and we can just reduce this one. As we mentioned, like beta and the x gamma actually can be combined together. But the eta is the value that for the error compensation, and then that's just this one actually can be number which sometimes can be very, very small. And also alpha, even though here we have lower bound and upper bound, and actually in the real case, actually we choose alpha to be very very close to 1. So and then it works really really well, even though in the result here we cannot show, especially if we want to show the result, we cannot use alpha to be too big, because if you can see here, alpha actually most of the time is it's probably will be in the order of 1 over C plus 1. And by C plus C, this number can be sometimes actually can be very big.
So,
So,
can I?
Mhm.
Can I see your quantization algorithm, quantization approach again? That one. So you're using this p-norm quantization, right?
Yes.
See,
Yeah, you can use others, but the p-norm is the one that we found very efficient.
But this quantization is like you sort of do the binary, not exactly. So x p-norm is not binary, but sign is binary.
Yeah, sign is binary.
I was thinking, but naively thinking. So if you say for my x, instead of do this, I do the binary expansion, but I don't just choose binary. I have a different bits. I cut down. Maybe I use 8 bits or 4 bits. Which one would be better or
Okay, you mean for some you choose like you use more bits for some variable.
I use more bits. Because x pnom here you use the whole bits, right? If you use a double position, then you use a 16 bit. I don't know how many, but I say I don't do that. But all the vector x, each of them I just cut down. Then of course there's a trade-off. Say which one will save more bits.
Okay,
it seems like this one you keep the direction, right? You keep the magnitude, and you keep the magnitude, but direction you have some trade-off.
Yes,
But
that's
using
true.
but using a different way, you made the direction might be more close to the right direction, right? Because
yeah, that's true. So, but in that case, actually, the data that you mainly communicate cannot shrink that much, because in this case, if you use infinity norm, actually in the numeric, actually, some of the examples we tested, actually we can reduce 95% of the data.
oh, interesting.
So in that case, I don't think you can do that.
But the p-norm here, you use the full bit, right? You use everything.
But that means for one actor, you only need to choose one. So
yes.
That means if you have 1,000, like X is 1,000, you just need to send one full bit.
Oh yeah. Sure. It depends. Okay.
Yep.
Okay. Yeah, you're right.
And actually, even though like for some applications, so if you choose even though from 16 or like 32 to 16 or to 8, maybe you will not see that much difference though. So that's actually why when we say like 95%, actually we compared with 32.
I see. Okay, thanks.
I have a follow-up question here. So is this p-norm quantization unbiased?
It is unbiased because of the Kasi.
Okay. So Kasi is random.
Yeah, Kasi is the random variable.
Okay. I guess you can say maybe combine this quantization together with maybe low bit quantization.
But of course you can add additional more, but that means like the sign will be probably has like more accurate information.
Yes.
But I mean, sort of follow up from Yang's question. This is Kasi I, right? You do have to have this xi, the absolute value of xi, and the p norm of x. So you have to compute this for your local, whatever local nodes, right? So
yes,
that one has no compression at all. And you need to, how do you create this Kasi I?
Oh, because your local, if you want to compress x, right? X is given, and you just need to compress x, so you know all these values, right?
Oh, because you you consider just that you don't need to send the data to the master. Okay, okay, I know. Okay, thanks.
This is like a general actually compression. Like recently, actually many there are also other biased compressions that I did not talk about here. But. And in fact, for some algorithms, actually biased works much better than the unbiased version, because biased actually can have more information there. So with this one, actually we can show the algorithm converges like linearly if the parameter choose and satisfies some conditions. and also for the non-convex version, and we can show actually the algorithm also converge. But this is the rate by the probably like the similar rate with the SGD. Okay, so let me just compare all these like several algorithms like the before DOR and also probably similar way. And actually, the algorithm that we basically that's all the algorithms that we talked about. So like SGD and QSGD, and then most algorithms before actually until like Diana, they only compress the gradient. So that's why even if you compress the gradient, you cannot reduce the communication from the server. So and after that, at that time, actually probably the same similar time, and then double squeeze and the store, they both compress the gradient and the model, and they choose different compressions. And then actually double squeeze use the biased compression. So in that case, for they cannot converge linearly though, even though they did not provide because they have some error there. So they use error compensation. So and also after that, you can see this is the convergence rate. Basically, the convergence rate of DOR is close to the distributed SGD. And then if you can see the quantities, that actually is 1/k, and there will be this is also like 1/k and plus b. There will be a constant b here. Okay, so but if you can look here, they are I think from this one they are very close. But let's see the result for the numerical results. So first, actually, we try to see whether the algorithm is really linear convergence or not. And then, so we try this on a very simple regional regression problem. And in this case, we choose also a different step size. And we can see here, and then we can see the linear convergence. Actually, the DOR and SGD and Diana will have the linear convergence. And then, however, and then the other algorithms, they will not have the linear convergence because you can here SGD is the gradient descent, or just a gradient. There will be no stochastic here. So and so if you just quantize the gradient descent and also a memo gradient descent or double squeeze, and then you can see here actually they will always like converge to some part, and then they will not go down. It's just because the constant step size. If they choose the constant step size, as we know, as explained before, the error cannot get in smaller and smaller. So that's why they cannot converge. And also double squeeze, actually, there will be one double squeeze which is diverge, actually on the left figure, and that's actually use the stochastic version, unbiased. But if you choose the double squeeze with top K, and actually it converges here. So that's why I said for the double squeeze, it seems that a biased version, like using top K, is much better than unbiased version. For unbiased, we just choose a random K. Also, we choose the p-norm quantization there. However, if we choose the step size to be smaller, and we can see here the double squeeze with random quantization actually converges to some point here. So that actually tells us that the step size matters for these algorithms, like for other algorithms. So the next one, actually, we just trying to see what is the data that to be compressed. And we can see here, actually, this is just trying to verify that our algorithm converge. Actually, the reason is we can see here, the data that to be compressed actually is getting smaller and smaller. So the left is the data that to be compressed at the worker node. And then the right figure is the data to be compressed at the master node. And we can see here, we only compared with the double squeeze and also DOR. And we can see the double squeeze, like data to be compressed, actually, they will stay at some stage and will not decrease for the double squeeze. And also we can see here, the problem for double squeeze with random quantization actually happens from the data that is from the data from at the server part, at the server node. So that's why because that's why the double squeeze cannot converge with gradient descent. And then next, actually, we tried this on the stochastic version, and then so we tried on some neural network stuff, and then we can see here the algorithms are very close though. So if you use the epoch and the training loss is the one that we focus on. Actually, the other one is the test loss. Actually, is about the machine learning applications. But we can see here, but you can see most of these algorithms are very close. They're not far from each other. Again, the only thing double squeeze with random quantization is not good. So that's actually what in their double squeeze paper they use top K. And so, but top K actually works much better though. And then for another deep learning algorithm, then that's actually it's very similar, and we cannot see too much difference here. Again, the only thing worse is the double squeeze with random quantization. So all the others, they are very close. So based on this result, probably we can see that no, even though if we choose the quantize the even though we compress the data, but the performance is very similar, or we do not see any performance loss here. Okay, so any questions so far?
Hi, Professor. I just want to ask a clarification problem. So is this on a decentralized problem or a centralized problem?
Centralized.
Okay, okay,
Yeah,
I see. Thank you.
Yeah, today's talk, I will not talk about decentralized algorithm, even though I have papers on the decentralized algorithm.
Mm-hmm. Yeah, thank you.
So any other questions? So the next one, actually, we are going to talk about, we just focus on the stochastic algorithm, because if we just use the stochastic version, and we do not expect that we will get a linear convergence, even though for strongly convex. So it's just because of the stochastic there. So we cannot compute the full gradient. Okay, so in that case, we assume that, of course, we assume the stochastic is unbiased and also has some positive variance. And then there are many different algorithms for variance reduction techniques, SVRG and Saga or Sara that can be used, and also our momentum method, momentum SGD, Storm, or root SGD or IGT. All these algorithms actually, so in this part, we are going to focus on the momentum algorithms. So we will talk about the momentum SGD, Storm, or root SGD. So in this case, we do not have any full gradient, because for variance reduction techniques like SVRG, you need to compute the full gradient. So that's actually one thing that we do not consider here, because if we do the SVRG, we can get the linear convergence. So I will not focus on here. And also Saga, you need a large memory there. And then also Sara, you also compute the gradient every several iterations. So this part, we will only focus on momentum method, so we do not compute the full gradient. So that's actually the part that we are going to talk about. And then we put all this into a general framework for the momentum SGD. So momentum SGD is, actually here, I just put this with one node, and with more nodes, actually we just need to find the average of all these values though. So xk plus 1 will be xk minus eta, and the running rate, and multiplied by the vk. And how to update vk is that here. So we have the vk will be equals 1 minus alpha k multiplied by vk minus 1 and plus alpha k gk. So because of we have the vk minus 1 here, so that's actually where we will have the momentum from here. And also by choosing different g here, and we will get a different algorithms. For example, if alpha equals 1, and then there will be no vk minus 1, there will be no momentum, and then this is a stochastic gradient descent. And then with momentum, we just choose alpha can be just a constant, so just the g is the gradient. And then with storm, actually we just add additional term here. This is not just a one gradient computation. You need to do 2 gradient computations. And then also we have the root SGD is that you need to you will change the alpha k. So alpha k will not be a constant. And IGT is that you need to do some weighted average inside here and then do the computed gradient. So these are all these several algorithms, but they all can be constructed into this framework. And then for this part, we are going to see in this case, how can we do the compression, and then we will not do the gradient checking or the gradient difference. The reason is because for the gradient difference, we have one assumption is that we want to make sure that the gradient will converge, and then we can develop another sequence that will be converged to the same point. However, in this time, because we always have stochastic gradient, so that means it will not converge. So in that case, probably we do not need to just use that accurate one, because that one may not be that accurate as well. So we can just focus on the error compensation. So that's why we will just focus on the error compensation here. So this is the recall that the error compensation, standard error compensation that we have before. So we have fk plus 1 will be equals xk minus eta q and gk plus ek minus 1. And then this is like ek. This is the compute another error here, update the error. And then for now, actually, I don't have time to talk about the row path filter, so you can ignore this part because this is not quite related to the main idea for this paper. So in this case, this is the standard error compensation. But let's see if we just add, in this case, if we add the momentum here, then what do we get, right? So let's see all these accumulations and see what we get. So if we assume that we start with x0 and we until xt, if there's no compression, but we have the momentum here, actually we can see this is the result that we will get. So xt will be x0 minus everything here. So we have alpha, eta, even though the summation of all these gradients. And of course, if alpha equals 1, then that is only SGD. So the left-hand part will be the middle term will be 0. So that's exactly what we have before. However, if we have the momentum, we can see here actually we need all these terms. Like this is the terms that comes from the momentum. So we need all these like g from the previous one. Okay, so and let's see what we can get, or how much error that we will get into this one, because if we do the compression, we want to make sure that we add a small error onto the result. So for example, if we just simply just compress on G, so this is just direct compression. Okay, so if we just do direct compression, and we will see this will be GS minus ES. And then because we get the GS minus ES, so by the way, because ES is the error that we did not send. So GS minus ES is the total, is the difference, actually is the data that we sent after the quantization. So we get GS minus ES, and then by doing this, and then we will see, okay, actually we have all these terms here. So that's actually what we can see. This will be the error term. We can see all these error term here. Okay, and actually, by the way, here actually we put all these G onto here. So if the red part actually the additional error from the direct compression. So that's one thing. And if we do the error compensation, is that we can have another. It's because this time we do not compress the GS. We compress the GS plus ES minus 1. So that's why we have GS plus ES minus 1 and minus the new error. So that's the data that we sent. And by doing this, actually you will see that this is the error that we get. And still, we have a term here with all these errors from the previous iterations. Even though this is smaller, but it's still there. And of course, if alpha equals 0, if alpha equals 1, then there is no momentum, then this red term will be cancelled. So that there will be no this term here. So that's why by doing error compensation, actually it helps. It helps comparing to the direct compression, because if the alpha equals 1, direct compression will still have the error. So this error will always like accumulate because the error will be added together. But if you do the error compensation with alpha equals 1, the error will not accumulate. However, if we do the momentum alpha not equals 0, also not alpha not equals 1, we will have this term here. And then the most important thing is that when we do momentum aggregation, we want alpha to be very, very small. So alpha is usually very small. So when alpha is small, then this value actually is big, actually compared to the last term. So that means like this term may dominate, sometimes can dominate the others. So because this is the error, this is summation of the previous error similarly. But here is only the error at the last term. So that tells us that, okay, we need to develop this new method to cancel these terms out. So that's actually the main part for this talk. So let's just see the new algorithm, the performance of the new algorithm first. So we tried this on different algorithm or different numerical examples, and we tried different algorithms like Storm and IGT. So for example, we can do a single compression, it's just the error compensation. And then we can see this, if we just do error compensation, and then the performance actually is very bad comparing to the Storm without any compression. However, if we do the error compensate the X, then that's, we can see which is much better, and also we can see get very close to performance. And then the reason is because we add a new term here, and then we will cancel that one, the term out. So that actually happens here. So instead of compress the GS and plus ES minus 1, and actually we compress the GS plus 1 minus alpha multiplied by ES minus 1 and then minus ES minus 2 and plus ES minus 1. So we add additional term here. And then we add additional term here. This is very similar to the momentum. Actually, we think about actually we also choose the momentum for the error term. So by doing this, and actually this term will be cancelled, and we can see the final error. And only happens is like we will only get the error from the last term. Okay, so that actually tells us that the error does not accumulate because the error will be only at some bound, it can be bounded at least. So because the error actually every time is just used to quantize the gradient. So in that case, we can say, okay, this is actually very good. And also, if we choose alpha to be small, actually this term actually is small. So that's actually can be even smaller than the stochastic gradient descent without any momentum. So that's why we propose the error compensated X. That's the new algorithm. So we just add the new term here before we do the compression. So this is the main idea for the error compensated. And then there are some convergence analysis, even though the convergence analysis is not that good actually. For some of the convergence analysis, we especially even though if you use if you use Storm or IGT, sometimes the result is even worse than the SGD or momentum from the convergence result. But this is the similar result with all the error compensation. They also have these similar results, but in the real performance actually is much better. So for example, you can see here actually. This actually I think this one actually we changed. There's no we have another version, so there's no t here, no to the power of t here. Okay, so but if you look at here, this is like a t to the power of like 2/3, and this is like a 4/9. But this is sometimes this is even worse than the SGD one. But in the real performance actually is much better. So let me just show some of the numeric examples here. In this case, actually, we test this on the ResNet 50, and we can see here, even using the momentum SGD, and then probably we can see like we do not see too much difference using the error compensation. However, if we choose the Storm, actually we can see this result can be better, and also IGT, and then we can see the error compensation actually can be better. But for the momentum SGD, it's very close for this example. Okay, so I think this is probably all my talk. And do you have any questions